Yes, good day. Today I want us to look at the photoelectric experiments, which are normally done using software simulations because they are difficult to do physically in the laboratories. For example, here you would be having investigating the effect of light frequency or different colors of light on the maximum kinetic energy, right? Then another one that is common is they can also look at the relationship between the wavelength of the light and the maximum kinetic energy. And in this case, on the x-axis, you'll be having the reciprocal of the wavelength, right? And your kinetic energy could be in joules, or most commonly it is in electron volts. So I think electron volts is the most common unit because they are smaller numbers to deal with for the purpose of drawing graphs. Right. Now the question that I want to address today is this one, where you have to write this equation for the photoelectric effect, which is photon energy, which is F H being Planck's constant equals to the wave function, the minimum amount of energy that you need to emit electrons from the surface of a metal, plus the maximum kinetic energy, which means the maximum kinetic energy that the electrons have when they just start to leave the surface of the metal, right? But before we go to that, if you look at this graph, you might find in the question paper, they might ask, what is this position P? Then you have to say that is that frequency there. You see this frequency? The frequency P there corresponds to the threshold frequency, which is the minimum frequency required to emit electrons from the surface of a metal. Right? And then if they ask you about frequencies that are lower than this, all these frequencies all the way are lower than the threshold frequency. So as you can see from the graph, no electrons will be emitted from the surface. So therefore, there's no kinetic energy to expect. So no kinetic energy from there. And then obviously, point Q will measure the work function. It will give you the work function of the metal. Right. So now this video is specifically to address learners struggle to change this equation into the form y is equal to mx plus c. And what I'm going to do is to start off by addressing a situation where f is the x-axis variable and maximum kinetic energy is the y, the output variable. And in this case, the inverse of lambda, or the inverse of the wavelength, obviously the units will be per meter, is the x-axis variable and the maximum kinetic energy. So I want to address those two. And then another question that they can ask is, they will say, what in this kind of experiment, what would be your independent variable? Obviously, your independent variable is, yeah, who can guess? Right, you're right. So your independent variable would be the frequency. It is the variable that you deliberately change in the experiment, right? And then obviously the output variable that you measure, is your dependent variable. So the kinetic energy max will be your output variable. If they ask about the control variables, a good control variable here, because you don't want, yeah, a good control variable would be the light intensity. But remember that with light intensity, if the light intensity, if you are using light intensity of a light, if the light intensity of the light is too small, the number of electrons that are ejected from the surface of the metal per second decreases. So the higher the light intensity, the more the electrons that may be injected, provided that the frequency of the light is above the threshold frequency. That is important. Right. Okay. So what you could keep constant here, let's say light intensity of 100 watts, that could be a good control variable for that experiment. Okay, let's go straight to the changing that to the form y equals mx plus c. So the first thing that you need to do is to identify your y, your c, and your x, the variable. So here, this is hf, right? Let me rewrite this because w naught plus ek max. Okay. So y-axis is kinetic energy maximum. So this is going to be my y. Good. And this is the constant. So, but I already know that this is going to be my c, because we said where the graph casts the y-axis is your work function. And somewhere here I'm going to get the frequency is going to be my x, right, for this graph. So this one is pretty easy. And your h maybe is going to be your gradient. Right, let's see what you get. So you can rewrite this in the form. So it will be ek, y is ek, right? If I transfer the w naught to this side, so this is, imagine that this is on your right side, so it would be hf minus w naught. As you can see from the graph, you read your work function. So it is done. So this is your y, h. If you do the gradient of that graph, it will give you your Planck's constant straight up. So if you do the gradient of that graph, it will give you a Planck's constant. So that's done. So let's do this one. Let's do this one. I can remove that one. Maybe let me remove this graph and do this one there. Right. If you do that one, I hope you are following. Then it means you have the same equation. We want 1 over lambda to be okay. This, remember, we just replaced f there with, from the equation of the speed of light, c is equals f lambda, so it's going to be we replace f there, so it's going to be h times c over lambda equals w naught plus the maximum kinetic energy. But again, I want this one to be my y, and we want this one to be our c, and 1 over lambda, so I should rewrite this one to h c times 1 over lambda, right? This one. So that this becomes my x. So now I can rewrite that to give me ek. Can I write here? Ek is my y max. That's y equals. Then that goes minus there. So it's hc times 1 over lambda. I hope you can see the mathematics there. Plus minus w naught. Done. So your hc, then your hc will give you the gradient. So if they say find Planck's constant, it will be simply Planck's constant will be your gradient divided by the speed of light. You see. So that's how you do it. I hope you enjoyed the kinetic energy might be electron volts. You can always change electron volts to joules. You know how to convert that. 1 electron volt is 1.6 times 10 to the power what joules. So I hope you have enjoyed this. Please hit the subscribe button, please, and or just give me like so that we can continue to share more of this. Thank you.